flu today. You're aware of that, right?
No.
That people are getting sick with the flu or have been getting sick. It's just like insane, in my opinion.
Are we dropping like flies?
Yeah. Okay, let's begin by going over this review type quiz that I wanted to go over last time but didn't get a chance to. This is not exactly like last week's quiz, but this week's quiz is not exactly like last week's. It's more like this one. And that's why I put it together for Tuesday. The only thing that I'm not going to have, I'm going to have you do something else on the real quiz. It's sketching, but sketching is never a bad thing. So this quiz happens to start off with sketching, which is just the two pi functions. So does anybody want to tell me what they have, how to sketch it, if they scribbled out their own answer?
What's that half? Yeah, it's pi 1. Yep.
So there's a pulse right at, centered on where?
0.
Okay. So minus 1/2 to 1/2 is what I'm hearing. Okay. And then the other one is centered on 4. And it goes from negative 3/2.
Sorry, 3.5 or 4.5.
Okay.
If we're going to your design for 5 hours.
5 hours?
I don't know. That's it.
Okay, so that's good. And now taking the Fourier transform of this is as easy as two sinc functions and what theorem? Time shift theorem or delay theorem. What do you prefer to call it?
Whatever goes by on my table.
Okay. I was inconsistent. My editors got after me on this one, so I've had to become consistent. But I like both names, actually. Yeah, time delay, time shift, delay theorem. Okay, so Fourier transforming term by term should be what you can do, and that's from linearity. So the first term is what? The pulse width is 1, so the pulse width comes out in front of the sinc function normally, but in this case it's 1, so it's 1 times sinc of 1 times f. Then there's a second term on here, which transforms from the delay theorem, right? So the delay theorem says, when you got a Fourier transform that, you get to transform the unshifted signal, which is pi t again. And then the delay theorem brings in what factor?
E to the minus j 8 pi f.
Okay, 8 pi f, does that sound right? It's 2 pi times the time shift, which is 4, so it's 8 pi f. Now, if I wanted to simplify this, how can I simplify this? Okay. So I can go 1 plus e to the minus j 8 pi f. Then what else might I do if I was really wanting to get neatness?
E to the minus j 4.
So I can build, what am I going to be building if I... Sine or cosine? Right? Because there's a plus sign in there. So I factor out half of that minus j 8 pi f exponential, and then that distributes a plus onto the first term, right, to make it balance. Can I do that all in one step? Euler's identity expansion like that? Or should I do it in 2 steps?
2 steps. Yeah.
I play in the big band, and that's one of the dance steps, right? When I play at the senior center, they have all the ballroom dancing steps, and that's one of the big...
Blue step. Yeah.
The blue step or the 2-step?
The 2-step, you can do the blue step.
Okay.
Blue stance.
sources, right?
No, that's string one.
Oh, yeah, okay. I'll give you that.
So, why would
Just
you-
some word of advice here for men only, I guess I'll say. Don't expect that when you get married, if you get married, that you won't have to learn ballroom dancing.
Oh, yeah.
My wife made me learn ballroom dancing and polka dancing too. The deal was she had to take an interest in downhill skiing and go skiing. So
Well, I would take that deal.
So why exactly would you want to do that?
do what?
Ballroom dance?
That's kind of off the subject,
Go
but
back on the
No, I
subject
think he
here.
was talking about that.
Well, it is Valentine's Day.
In the spirit of the day.
Why would you even take it this far? Just put it in just an complex exponential multiplied by a cosine wave.
okay, I'm going to show you in a second. So now now that I've got this into this form, I have to put a 2 in the front, and then I can cram a 2 down below there. Now I've got the cosine in there, right?
Mm-hmm.
So and this is going to be 4 pi f sinc f e to the minus j 4 pi f. The reason why I would want to do it if I was doing some analytical modeling would be a lot of times you're interested in just the spectrum magnitude. So if you're looking at just the magnitude of this, you would be able to focus on that. Magnitude of that would go to 1. And you'd basically know that you've got a sinc function magnitude, which has got the humps in it, and then you've got a cosine that's at a lower frequency or a higher frequency that's weighting against that and causing some additional lobing structure against it,
Okay.
which you can't as easily see in the other form.
Yeah.
Not as easily. If you were doing this in MATLAB, though, you could stop at the first line and you could do the plot in MATLAB without having to go further. But sometimes, there's a benefit to saying it's a sinc function weighted by a cosine. I mean, that might mean something if you wanted to describe it in words. Okay, the last part is the new innovation for this week's quiz, too, to say rather than just doing an out-and-out convolution, I turned it into a linear systems problem where the visual here is that there's a system that has some impulse response, and you're driving the signal x that we just looked at through the impulse response. And I worked it in the time domain, kind of like the way I worked the last week's quiz, but you could also work this in the frequency domain if you wanted to. Does anybody want to pick a way that they would like to go? Time? Okay. You agree?
No, I think time domain's easier.
Okay.
Well, think about it. I think it must be.
It took 3 lines.
Mine's. Sorry. It's just I read out 6 steps.
So you got to convolve 2 different pulses, but they're all the same width pulses. And as soon as I get done with this, we're going to go look at something different. I'm getting tired of looking at rectangles with rectangles, so there's something else that we're going to do in the notes that will not be a rectangle. So again, you could start from scratch, or you could start from some a priori knowledge, namely that you have a triangle involved. My preference is to take the easy path because once you learn enough about something, you don't have to go back and reinvent the wheel again. But you do need to clearly state what your assumptions are, especially in this, unless I say show all your work, I'm willing to go with, lesser work. But if you just are totally a daredevil and just write down the answer, then you take your chances, right? If there's no work shown. So what I would do, though, is I would, like I did before, I would say I know that this convolved with this is rectangle with a rectangle is just what? A triangle. Normally it's going to be, the pulse width is going to be involved with that, right? In other words, if this had a tau in here, then it ends up that it's tau triangle, getting ahead to the Fourier side. Now, I guess the reason why I'm pausing here, just to make sure you don't get careless, because like I was talking about in my office when somebody came in a little while ago, when you have things like 1 floating around in a problem, it doesn't help you figure things out because it actually it's hidden what it's doing. So where does that tau come from? Just to be clear, in the right side there. Remember, in the convolution, if you're thinking about sliding this pulse past the green pulse, when it's perfectly aligned, it'll be sitting right like that. And then this is minus tau over 2 to plus tau over 2. When you integrate that, you're taking the area of that overlap. So you have a width tau pulse of amplitude 1, and that area is tau, right? So that's where it comes from. Okay, so now what you can do is just start writing down what the answer is supposed to be with a little pause, I guess. The other thing would be, I'm just going to do it like this. What would this convolution be if there's a time shift?
In the triangle.
Okay.
Same negative T0.
So this case tau is 1, so I can drop that by the wayside. So this would be t minus t naught over 1.
Correct.
How could I prove that without having to resort to a convolution integral?
Use Fourier transform.
I could use Fourier. How about another idea?
Draw.
Well, I can draw pictures, yeah, but how about a mathematical way?
You're not going to have your peak until perfectly overlapped, which is going to be at.
What can I convolve easily without getting too involved? How can I get that pi of t minus tau more readily if I wanted to? What can I convolve that with?
Oh, yeah, the delta.
Okay? And I know anything convolved with the delta function gives me that anything with whatever the delay is that the delta has. So hopefully you got what you wanted before I erased it, because I'm just wanting the space. So I could actually get there by saying it's pi of t, because of the associativity property of convolution, that should also hold, right? I can distribute and associate things with convolution. So I could go back to it. I could say that piece in the square brackets follows from the first step, and then I could just take that triangle and convolve it with the delta function and shift it over. Does that sound good? I'm just trying to show you sort of forwards, backwards, sideways, all the different angles that you can look at it from. Fact of the matter is, not everybody's brain works the same, and everyone's going to see it slightly different. And that's a form of diversity, I guess you could call it, in the sense of how you work problems. And when you're wide awake, you might see it one way, and when you're half awake, you might see it another way. Hopefully, you still see it, though, which is a struggle. I know for myself, when you get tired, you don't see things right anymore. Okay. Trying to get fancy with my erasing tool, and that didn't quite do what I wanted it to do. So now that I have those pieces put together, I can pretty much just guess I should just get rid of all this, since we kind of know how that works out. So you have two triangles, one shifted over by 4. And the thing about the triangle, whatever the memory aid is, think that the triangle comes about in its definition because it represents the convolution of two equal width rectangular pulses. So a triangle has got a base width that's twice what the argument is of the triangle function. Normally the triangle would have the tau sitting in here, and there'd be a tau down below here. So the full base of the triangle would be twice that tau value. So when we draw this thing out, it's going to have the two triangles. And this is going to go -1 to 1, which is twice the original rectangle width. This is going to be centered on 4, and it's going to go minus, or not minus, but 3, 2, 5. And the height going all the way across there is still just 1. And that's controlled by the fact that tau initially was 1. Any questions? I shouldn't spend this much time on it. I'm trying to get you bored stiff, I guess, so that now you can just say, I'm never going to have a problem. What's that?
Can all of our quizzes be like this?
Oh, no. This will be the last, well, yeah, I shouldn't say exactly. We're about ready to get close to chapter 3, if I could go fast enough and wasn't giving a quiz later, but that's the way that is. What I want to do is go back and look at an example in the notes that we didn't look at because I wasn't really in the mood to look at it, but because we're looking at linear systems and we need to look at something more than just rectangles when we have linear systems. This was an example that appears on page 256 under just convolution, but this is a more important convolution because we're going to be looking at the RC low-pass filter here. In other words, this. Oops.
So we're revisiting this today?
Yeah,
Okay.
we're revisiting it today. This has got a relationship to that circuit. And we'll be looking at that in the further up in the notes, but I just thought I'd go back and just review through this convolution since the answer to this is useful in this particular part of the notes. So this is finding the step response of this exponential impulse response is the way I want you to think of it as. So you can think of this as being x of t, and this is the impulse response. So this convolution is not quite as, well, it's actually easier than the rectangles, but it's got a certain it's got properties to it that are different than the rectangles. Remember I said the convolution support interval is always the sum. It starts at the sum of the two starting points and ends at the sum of the two ending points. So now we've got a different situation. So this is, by the way, is lowercase y. So what would be the support interval on the output, just before we get started, to make sure we know what we're going after? If I say that rule applies always, and it does,
Negative infinity?
well, look at what you've got there. Both of them start at 0. So if the convolution output starts at the sum of the two starting points, it starts at 0.
Yeah.
And where does it end? because infinity plus infinity is still infinity. So it starts at 0 and ends at infinity. So we know just from the get-go, just as a reference, we start 0 and infinity. I think it never hurts to at least have that in your mind. If you don't take the time to write it down, at least you're thinking about it, so that if you start to get something squirrely that doesn't fit to this, you can at least put on the brakes and come back and say, I made a dumb error. Because one of the things I don't like when I grade papers is seeing somebody do beautiful work, but they got off to a bad start, and then the error just propagates all the way through the end, and it's disappointing, I guess, to say the least. You get partial credit, but it'd be nice to catch errors before they get worse. Okay, so when you work this type of a problem, both of them are semi-infinite, so there's really, from a personal preferences thing, there's really no, in my mind, there's no strong preference to whether you're going to flip and slide the step or flip and slide the exponential. What I'm talking about is the way I'm set this up is I'm doing this as x of lambda times h of t minus lambda d lambda. That's the form of the convolution integral. So I'm doing the flip and slide on the h of t signal. So because it's an exponential that starts at 0 and goes off to infinity, when it flips over, it spins around, and now it's running in the opposite direction. And t on the lambda axis is actually 0 on the original t axis when I flip it around. So if the signal was doing something like this originally on the t axis, I flip it and it's doing something like that when it's flipped, and then when I slide it back and forth, this just becomes t. Because that critical point there is when the argument is equal to 0, so when t minus lambda equals 0, that's when lambda equals t. So that's another way of thinking. That's how come I know that value right there is t. So now as this moves along, as t increases, it eventually overlaps. But when t is less than 0, there's no overlap. So that was the reason why I say the output is 0 for t less than 0. When t is greater than or equal to 0, then there is some partial overlap, and it holds like this for forever, because this tail out here goes back to minus infinity. No matter what t is, as that pulse slides across, there's always a tail that's hanging out on the negative lambda axis. But that's okay. It just tells you, just makes it clear that your limits are set from 0 to t, and then you integrate that out and you get the waveform that's shown right here when you do the integration. And normally the tradition is to summarize everything into one piecewise continuous function. So here there's only two pieces, so the step function is useful for putting it together. If there was more than two pieces, then you'd write a curly brace and say, this for this for this, and 0 otherwise, or something like that. So it's two pieces, and this is a very familiar output because this is a step driving an RC low-pass filter, and you know from being in the lab that when you hit some low-pass, the capacitor has to charge up from 0, initial conditions, and it doesn't happen instantly, but then it reaches steady state. The capacitor is an open circuit. The resistor is not pulling any current, so you see exactly what the input was at the output. Does everybody think that way from circuits and electronics? Yeah. Every skill or everything that you learn in any class that applies to waveforms and signal and system models bears down. You don't forget one thing and not use it, so it's okay to think, if this is a circuit model, that's what it is. Another way of looking at it, though, is that eventually so much of this area, this green area, is being integrated that you're essentially integrating that entire exponential, and that's going to integrate to what? Looks like I might have a sign error in here too. I do see a sign error in here, right? Or no? Alpha is supposed to be less than or greater than 0, right? Yep.
So this one remains true if it's a step function that lasts for infinity?
Pardon me?
This only is true for a step function that lasts till infinity, essentially?
Yeah. Here's what I got confused by. If I would multiply this out, I would get more along the lines of what I wanted to see. It's in the next line down below, but I have a over alpha times 1 minus e to the minus alpha t. And as t goes to infinity, that's the decaying term, so I just get the alpha over 2, or a over 2, a over alpha coming out of here. So, any other questions? I'm going to move forward in the notes. I'm going to look at a few properties that we didn't get through last time, but one of the things, the main thing we talked about was linear time invariant systems. The convolution integral gives us the output from the input in terms of the impulse response. And that was these two variations right here. The next thing is just recalling some things from linear systems, namely stability means that if you have a bounded input, you have a bounded output. And there's different ways of proving stability for a system, but if you have a linear time invariant system, there's a theorem that you go through in linear systems that says this thing is true, namely that the integral of the absolute value of the impulse response, if that's less than infinity, then you're stable, and it's if and only if, so it goes in both directions. Those of you that have taken controls or remember other things that you did probably in 3205, this eventually also has other implications, which I'll just briefly mention right now since I'm on it. And, well, maybe does anybody remember what any of those other implications are? This is the core theorem, but from this theorem there's a couple other nice properties that come out. If you don't remember, I'm okay with it, but I'm just thought that if you remember, just see if it's sunk in at all.
But the transients take over?
Well, if it's stable, the transients die out. They go away.
Right.
But there's a frequency domain view, and then there's an S domain view. We're not doing the Laplace transform until we get to phase-locked loops in this class. We will be doing some stuff with the Laplace transform there, but
There are poles that need to be stable.
so they have to be where?
Hand side,
They have to be in the left side of the S-plane if it's a causal system. But the more and that's the only type of systems we really deal with, are causal systems. We're going to talk about that in a second too, but the more fundamental thing is that the Fourier transform has to exist, because that's on the j omega axis in the S-plane, and that's what we really need, and that's equivalent to this blue boxed equation right here.
So it's just basically a further.
They spin off of this property. But the thing that you remember is what you just said, the poles in the left half plane. That's what most people would remember, for causal systems at least. The transfer function follows from the convolution theorem for Fourier transforms, and it just says if we take the Fourier transform of both sides of this relation, now that we have an impulse response as opposed to just something that we're convolving with something else, that gives us that the spectrum at the output is the spectrum at the input times the transfer function or frequency response of our system. And then from that you have the definition that it is the Fourier transform of the impulse response. So that gives you the frequency response of a system. So Fourier transforms give spectra for signals and frequency responses if it's a system's impulse response. Same idea, same Fourier idea, it's just you interpret it differently. They both are very valuable. They're used to help you design systems. But if you're in the business of building filters, the frequency response is probably one of the favorite topics then, because you want to sweep the frequency response of the filter and see what shape it has. This last line down below here is just the statement of the convolution theorem. So now causality, since I mentioned that, here's a reminder of how that works. A system is causal if the present output relies only on past and present values of the input. And in particular, the output doesn't anticipate the input. So for the linear time invariant system, that is reflected through the impulse response by this property right here, that the impulse response can't turn on until t is greater than or equal to 0. It has to be 0 for t less than 0. Otherwise, you're anticipating the arrival of the input. So a quickie little example of that is if, suppose I'm going to drive the system with a step, convolve it with h of t. So I'll set up the convolution integral right over here, and I'm going to suppose that's h of lambda, and then sitting right in here would be u of t minus lambda. So as I increase t, I'm eventually going to engage the impulse response. And I'm showing the impulse response having a little bit of a tail for t less than 0 and then a bigger, longer tail for t greater than 0. So if I'm driving a step function into a system that's causal, the step function turns on at t is equal to 0, right? So the input arrives starting at t is equal to 0. If the system is causal, can anything come out the output before t is equal to 0? Because that violates causality, right? So see the little tail that's sitting over in here. When I eventually bring t up closer, in other words, I bring this thing right up into here, t is still a little bit less than the red 0 there. What's starting to happen? I'm going to start to get output values, right? Because I have a little bit of overlap. And by the time I reach t is equal to 0, I've definitely got an output. So in order to ensure that I don't get any outputs before the arrival of the input, I've got to make sure that the impulse response is 0 for t less than 0. Now in electronic networks, no problem. You can't build an electronic network unless you have some, unless there's something to do with Einstein's relativity theory, I guess. And I don't have a knowledge that has grown since I was in college on that one, but I guess you can have a causality issue with that if you take things to the limit. Now in digital signal processing, though, you can easily model things that are non-causal and set those up in simulation. But even so, in real modeling on the computer, you can't really have a truly non-causal system in a real-time sense because you just can't predict the future. You know, people want to do that. I know a guy that constantly is using signal processing ideas for his investing, trying to figure out how he can take, past performances of stocks and get trends, and I think people have wanted to do that for a long time, saying we can be really intelligent and we can predict a trend and know when to buy and when to sell. Any of you?
Does it work?
I don't know. He's always asking me questions about filters and other things. He's constantly working on it. Well, you work with the data, the time series data. It's digital signal processing,
He does
actually.
stats pretty well too.
Yeah, he does. He has a master's in operations research, so he does linear programming a lot for energy futures for a company. Linear programming is a technique to solve a optimization problem. And the futures idea is for power companies that want to buy and sell power. They figure out, where they should buy and sell it so that they come out ahead for the investors. So it's a nonlinear programming technique. So he writes software all the time. This is his side activity because he's a bachelor and he just lives at home. He's an older gentleman. He's been doing this all his life. He works when he needs to work, and then he messes around with his investments in this software. Some of you are probably going to do this too. And prior to the stock market crash a few years ago, there were a lot of people in, engineering, especially people that had backgrounds in some signals and systems and statistics, that were going and leaving engineering to go work on Wall Street because they were lured by the prospect of big money. So, and I believe it'll start happening again as things continue to improve in the economy. People will be lured by some of that, thinking that engineering is just not good enough. You got to do something better with your skill set. Any questions on that? I think this is in the book. I'm not remembering exactly where it is. Basically, this Paley-Wiener theorem says that when you come to design a filter, there's limitations on what you can make that realizable causal filter do. And the summary that I have down here is, this is probably the most important one. The first one is that if you're trying to build a filter and make it causal, you cannot have a finite band of frequencies where the frequency response is zero. That's the ideal, right? You'd like to be able to pass a bunch of frequencies here and then take these frequencies out here and totally shunt them down to zero. But this theorem says that with a causal filter, you cannot do that. Now, one of the things that is allowed, though, and I'm just going to sketch this out here. One of the things that is allowed, if you have a cutoff frequency here, FC, this model does allow you to have a pass band with some ripple in it, and then it says you can touch zero at certain points. Because that step, or that limitation 1 says over a finite band. It doesn't, isolated points are okay. So there's certain types of filters that will allow ripples in the stop band, and they can be close together and they can be fairly dense. And that comes from this theorem if you want to be causal.
This one actually does touch zero there?
Yeah.
Oh, wow.
I was going to bring some filters down today, but I forgot. The microwave filters are sitting on my desk as examples. That would be like an elliptical filter is one of those types, and a Chebyshev type 2 filter. You played around with some of these in 3205, right?
Yeah.
Maybe, did you talk about any of this deeper theory, the fact that you can and cannot? So you've seen it before then? Yeah. The Butterworth has a monotonic pass band and stop band. Chebyshev, though, allows ripple in the pass band or the stop band, and the elliptic puts ripple in both bands. The elliptic is the optimal in the sense that it guarantees, the elliptic has the most rapid transitioning if you're trying to define a band of frequencies where you're transitioning from, say, right here down to here. It's the narrowest with the elliptic. But the elliptic has some pretty bad side effects too. And Robert, in your design team, that's why I commented on the filter that you have that you're planning, and I still didn't get any response back from Andrew, but that's one of the things you can get into, is having too much distortion introduced by having this filter put in there to try to drop very rapidly in a small little transition band, which is what you get into when you're thinking of the way CD quality audio has to be represented. It goes up to 20 kilohertz, and the folding frequency is at 22.05 kilohertz. That only gives you 2.5 kilohertz to drop like 80 or 90 dB, which is really hard to do with a low order filter. And then you end up putting a lot of distortion in, and that's actually one of the last topics of the chapter is distortion.
The same way of going in and the same way of coming out now, going in on the deck.
Okay. Okay. I'm not looking for a status report from you guys, but the distortion is something that is more apparent when you've got, you know, a wideband source. Maybe we'll get to that before it's quiz time today too. So some other properties. The frequency response magnitude is even. The phase is odd. That just follows from Y. I mean, so it's real, and it's just follows from the Fourier transform properties, right? For real impulse response. For a real signal or real impulse response. Other properties involving spectral densities would be the energy spectral density at the output is the magnitude squared of the frequency response times the energy spectrum at the input, and the power spectral density would pick up the magnitude squared of the frequency response times the input spectrum. Now, a specific example that I sort of started to go through earlier, and I'm going to come back to the results from that convolution, is just to work a little example is an RC low-pass filter, which, how many times have you seen an RC low-pass filter in your life? But if you're a programmer type person, what's the famous programming first program called? Hello World, right? So this is the equivalent, I believe, for electrical engineers, the RC low-pass filter. If that seems fair, at least. It's nice, though, because the math is easy and it displays a lot of nice properties. So when you see this circuit and somebody says get the frequency response, without looking ahead, what's the most favorite way? Somebody just say, what's your favorite way of getting the frequency response? Using which techniques, though? Fourier, Laplace, or AC steady-state circuit analysis?
Oh, that was definitely no Laplace.
Okay, so if you go the Laplace route, then what do you have to do once you have it? Okay, or J2 pi f. Okay? And that assumes that the Fourier transform exists, because by plugging in J2 pi f, you're evaluating it on the j omega axis, which means it has to be stable, like I was saying before. But for this circuit, it's passive, so it's stable. What's the least favorite way? It's, okay, well, I mean, probably about the least favorite way would be what? Back in circuits 2205, yeah, differential equations. This is probably the first way that comes to mind for me if I want to get there, because I know it will work. This is the AC steady state. It's just basically an impedance, voltage divider idea. But the S domain is a little bit cleaner in that regard. 1 over SC all over R plus 1 over SC, and then you have to make the substitutions to get in there. And this is the property that you're well acquainted with, 1 over 2 pi RC for the 3 dB frequency. The differential equation is not as much fun, but if you go that route and write it out from like circuits 2205, I guess, is where you learn to do that. You can apply the differentiation theorem for Fourier transforms or Laplace transforms and still arrive at the answer just the same. Right?
Yeah.
I mean, you saw that. I don't know where you saw that, though. Did you see that in 3205 or never?
2205 this one.
But you didn't do Fourier in 2205, right? So you have a disc.
We saw the beginning of it in 2205, and then we actually solved it using differential equations, but then we didn't apply Fourier to it.
Yeah, that's what I figured. I figured all these things out when I had to write this one chapter I have in the book where that you do something, but you're not really calling it a Fourier, so I got at it from AC, steady state, the idea of applying a sinusoid in steady state, and you can arrive at it the same way without calling it a Fourier, because it amounts to something that's more based in circuits. So these are the magnitude and phase responses of this simple circuit. Like I said, it has the 3 dB frequency or the 0.707 gain at the cutoff frequency. I don't have it noted on here, but what's something else that you remember about this circuit in the phase plot? If I was to extend this down. I don't have it drawn quite accurately, but what is that value?
Higher vertex, higher forward,
Yeah,
negative higher forward.
which is 45 degrees, right?
45.
And it asymptotes towards minus 90. Of course, you saw this on the network analyzer in the lab, right, when you did the plots? That's satisfying to see it on an instrument. It's like an instrument was designed to follow the math. Which came first, you know, the chicken or the egg?
I did the math.
Okay. Okay, the example problem of the convolution is putting in a pulse and getting the pulse response to the RC low-pass filter. So this particular pulse looks complicated and messy, but it's trying to get a pulse that starts at 0 and ends at t and has an amplitude of A. You're right, it's called a causal signal. That's kind of a causal impulse responses are 0 for t less than 0, but a slang interpretation of that is to say a signal is causal if it starts at t is equal to 0. Causality doesn't apply to signals, right? It really doesn't make any sense, but in the slang terminology, you could say the signal is causal, just to say that it starts at t is equal to 0. Or if you have a better English language explanation for that, I call it slang. Engineers have a lot of slang terminology that I also found out editors of books don't like either. They're too English perfectionist oriented. Okay, so if you want to get the frequency response, you just get the spectrum of the input and multiply it times the frequency response of the filter, and you get the sinc function times the one-pole filter. If you wanted to get the output in the time domain, the bright idea might initially be, let's just inverse Fourier transform this, or inverse Laplace transform it if you think that might be better. And you kind of get a little bit hung up. Actually, in the Fourier domain, you get hung up probably worse than you do in the Laplace domain.
Yeah.
So it's frustrating, right? Because you come to believe that the convolution integral convolution theorem can always get you out of trouble. The Fourier convolution theorem does not work well with this problem because you have a sinc and you have that 1 over 1 plus j f over fs, and it's just kind of like if you look at the math of trying to inverse Laplace or inverse Fourier transform that, you say, I don't know how to handle that, right?
Yeah.
Because the sinc goes back to a rectangle, all well and fine. The 1 over 1 plus jf goes back to the complex, or goes back to the exponential, but if you mix them together, it's like you don't find that in a table anywhere.
So how did you find h of t then? Is there?
I don't believe there's an easy way. I mean, myself.
But it says that you found it from the Fourier transform tables.
Now, I found I can find the impulse response.
Oh, okay.
I can get that piece of it. What I'm hinting at is I'm saying I'm going to bail out on this. I'm going to say I'm going to just go after this by the old-fashioned way of just convolving.
Oh. Okay.
Now, if you went to the Laplace domain, you could use the delay theorem or time shift theorem in Laplace, and then you'd have, is it called the S shift theorem? No, it's a different one. You'd have a way of getting at it, but I'm not going to go off that way because I don't have that set up here in the notes. All I'm saying is that be on guard. You can't always win with the Laplace transform and the convolution theorem. I mean, you can't always get there easier. You have to be flexible and say, sometimes I just can't go that way. In this case, another way that can get you there, though, is the problem that I worked earlier. The example was this guy right here. And all I have to do to make this one match up is put in a scale factor. Basically, I have to let alpha equal 1 over RC, and then I have to also drop in a scale factor 1 over RC up front. And I'll be able to utilize that. And then from linearity, I can break the input pulse up into a difference between a step that turns on at 0 and subtracting a step that turns on at t. And that creates the rectangular pulse. So one of the beautiful things about linear systems is I can apply this input and get this output, and then I can apply this input and get this output. So I just form a linear combination of the individual inputs at the output, so I subtract those two. Then you could do some simplifications on it, which I didn't do. I just simply made some plots. I think I did these in Mathematica. And this is the book's idea of trying to show you that how does the spectrum relate to the time domain waveform. So the spectrum at the input is the red. The green is the filter's frequency response, and then the blue, which is shrunk the tightest, is the result of multiplying the spectrum times the frequency response. And when you're doing that much spectral shaping, the filter is really impinging upon the spectrum of the input in red. You get this case over here, a lot of distortion on the pulse. The pulse comes on, the output time constant is so large, it's 2 times the pulse width. So you slowly charge up. By the time you're starting to make some decent headway, the pulse is gone, and then you're decaying back to 0 again. I mean, you've seen that in the lab probably. Your time constant's so big that the pulse gets really battered up. I mean, if this was digital logic or something, this would never cross the threshold for a 1 and a 0 because you just had too much capacitive loading on the line or in the networks. The second example, though, is the other extreme where RC is the pulse width divided by 10. So your time constant is only 1/10 of the pulse width. So now the spectral shaping that the filter throws on is much wider. It's the green one compared to the red. And what comes out of the filter is very minimally shaped by the filter, and you're getting a fairly fast rise time going on there. You've seen all this stuff before, but you haven't looked at it maybe recently, so that's why I'm just sort of going through it like that. Okay, the next topic is just saying what happens if I apply a periodic input to a system and looking at it in the frequency domain. I have the line spectra, or I have the Fourier transform of the Fourier series we looked at before, or just simply we had that the spectrum was the line spectra with the Fourier coefficients. Or the other thing that we remember that we did the other day was this is F naught times P of n times F naught, where little p is 1 period. Oops. Computer glitch there. Didn't respond. P of t, remember, is 1 period of the periodic waveform. That's how you could get the Fourier coefficient. At any rate, you multiply that spectrum times h of f, and it samples the frequency response at where those harmonics occur, n f naught. And then that also would be the way back to your Fourier series representation if you wanted to carry it along like that. This also is the equivalent to the AC steady-state circuit analysis model that you learn about in circuits, where you only have a sinusoid present. That would be, so you only have the fundamental present, but you would have the frequency response magnitude gets sampled at the frequency of the sinusoid, which would be, say, n time or f naught if n was only equal to 1, and that's what shows up as an output of a circuit, let's say. In circuits, you never applied more than one sinusoid simultaneously, right? Or at least I don't remember when I took circuits that we would do that right away. Or at least in the lab, when you do a circuits lab, you have a sinusoid generator, a network, and then you measure points in the network. True? Or, I mean, is that still stuff that you do?
Yeah, I think it was just a single thing.
But it's a linear network, so you could have a superposition of sinusoids. Okay, one of the things we'll get into next week to wrap up the chapter is distortionless transmission. And this just gets into what constitutes a system with distortion. And there's different types of distortion. There's delay distortion, there's amplitude distortion, and phase distortion. And the starting point is to just consider a simple system that purely delays, and a pure delay is acceptable. In other words, if the output just comes out delayed by t0 seconds, we're content with that as long as we can manage the time delay. But if the output comes out with different types of distortions, like I said, amplitude or phase or nonlinear distortion, then we're not okay. And I guess one of the last, looking at my watch here to make sure I provide enough time, one of the types of distortion that you might think of, delay distortion at least, is what happens if a signal goes into a system and a signal at one frequency gets delayed, say, by a microsecond, and another signal at another frequency gets delayed by 2 microseconds. It turns out that is distortion, because if you think that those components at the 2 different frequencies were needed because they're the waveform of interest, and one component gets delayed by 1 microsecond, the other by 2, that's called dispersion, where some parts of the information are dispersed over time or smeared over time. And that's what's called the delay distortion, or that's getting into the idea of group delay, which is this next topic right here. What made me think about that, though, is that, remember the fiber optic spool that I brought in the first week? When people were first discovering fiber optic could be used for carrying lots of information, there was the design of the fiber optic cable, which is like a cylindrical waveguide model. That's the way it's modeled in waveguide theory. Then there has to be an outer cladding of some dielectric material so you can get internal reflections. It goes down to the stuff you learned in physics, where you have an interface between 2 different indices of refraction, which is like dielectric constants, I guess. So you get internal reflection, so the waves are bouncing, zigzagging through the fiber optic pipe. But then they discovered that the material's properties were such that there was dispersion if you tried to send a wideband signal down, so the pulses would get smeared out in time. But then what they came along with is the process to make fibers like the one I passed around, which was what's called a single mode fiber, which only supports a single mode when you launch into the waveguide, so you don't get these different modes, multi-mode, supporting with different, or having different delays, which cause the pulse dispersion. So that fiber was an example of some of the early generation single mode fibers, and that's pretty much what's used in the trunking, for our internet, because they can carry so much data, because pulses at multiple, giga sample or gigabits per second can go into those fibers and not get smeared out. Gigahertz is 1 over that is 1 nanosecond, right? So pulses that are less than a nanosecond, they're just hundreds of picoseconds, can go through and not get smeared out. That was, the innovation was coming up with the fibers that would support that, and then the laser devices that could launch light pulses into the fibers. That's our internet lesson, I guess you might say. Okay, why we have the internet. Now, why did the campus come under attack yesterday? I have no idea, but it was very frustrating for me, and I'm sure for you. I wanted to get the video lecture up on Tuesday night after class. I wanted to do other things. It was just dead when I got home, and I came to campus yesterday morning just to put up stuff, and I got it up there, and then when I got back home to work on my editing, I saw the emails coming out that, which I guess you guys saw too, that we were under attack, and we're still under attack.